Okay, Chapter 6 covered discrete probability distributions, and now we're going to look at continuous probability distributions, and the most common one is the normal probability distribution. Section 7.1 covers the properties of the normal distribution. So our objectives are to list the properties of the normal curve, explain the relationship between area and probability, interpret probabilities and proportions, use TI-84 technology to find probabilities, proportions, or percentages given specified values. So again, these are continuous probability distributions. These are things that you measure. Our random variable x is a measurement. And here's a very important note. The sum of the area under the curve is equal to 1, which is the same concept as the sum of the probabilities in the table must equal 1. So we saw that in the discrete probability distributions, that the sum of the probabilities, of course all of the probabilities are between 0 and 1 inclusive, but the other requirement is that the sum of the probabilities in the table must equal 1. And now as we look at our diagrams, we're going to be looking at area under the curve, and the sum of that area under the curve must equal 1. So to understand this idea of area under the curve, we're going to look at the uniform distribution, which we just briefly saw at the end of 6.1. The uniform distribution shape is a rectangle, and we know how to compute the area of a rectangle. If you think of the normal curve, that bell shape, there's not an easy way to calculate that area. Our TI-84s are programmed to do it. There is a formula for it, but it's not a simple formula like it is for the rectangle. So we're going to look at the uniform distribution first, just to make that connection, understand that concept of area under the curve and the probability. Okay, in example 1, the random variable x is the weight of the salad prepared by a customer, say at a salad bar, and the probability of x is the probability of each possible weight. All probabilities are equally likely for weights between 6 ounces and 16 ounces. So what would this probability density curve look like? Well, of course, it has our vertical axis and our horizontal axis. The vertical axis is our probability, and the horizontal axis is our random variable x, and these are ounces, the weights, all the different possible weights, and they tell us it's equally likely between 6 ounces, so I'll mark where 6 is, to 16 ounces. And they all have the same probability, and that's where we get this rectangle. So for every measurement, all the little possible in-betweens, 6.3, 6.7, 9.2 ounces, have the same probability, whatever that is. They haven't told us what it is, but it's the same. Well, they've also, the thing we do know is that the total area under this curve, and we consider this the curve in this diagram, is 1. We know that. It has to be. We also should know from basic geometry the formula for area of a rectangle. Do you remember what that is? Yeah, it's length times width, right? To get the area of any rectangle, you just multiply the length times the width. So we're supposed to find the uniform probability. We're supposed to find this uniform probability for all of the x's. Well, the length. Do we know the length of this rectangle? It's not 16, right? Because it starts at 6. So it would be the difference between 16 and 6, which you probably already computed, 10. That's the length of that rectangle. Width is what we're trying to find, right? But we know area. It's 1. So if we use this formula of area equals length times width, then we can plug in 1 equals 10 times W. And the only thing we don't know here is W. So you divide both sides by 10 to get W by itself, and you get 1/10 is W. So the width is 1/10, or as we usually use decimals, 1 divided by 10, 0.1. So now we know P of x for all possible values between 6 ounces and 16 ounces is 0.1. So now we have the width of this rectangle. And we can answer questions about all these different weights in here, these random variable x's. We can answer questions about what's the probability of less than this, greater than that, in between these two numbers, because it's just going to be the area of smaller rectangles inside this big one. So for example, find the probability that a customer prepares a salad that weighs more than 12 ounces. So the probability that x is greater than 12. Well, that's just the area above 12. So let's mark off just wherever we think 12 is. I don't know. Maybe it's here. It's probably not quite right, but we're looking for this area. Again, it's a rectangle. So if we can get the length, we know the width, we've got the area. So the length of this rectangle will be 16 minus 12. That's the length. The width, of course, is 0.1. We already know that. There's the width. So we get, what, 4 times 0.1, or 0.4. So the probability that a customer prepares a salad that weighs more than 12 ounces is 0.4. Find the probability that a customer prepares a salad that weighs between 10 and 13 ounces. So the probability that x is between 10 and 13. All right, so where would 10 would be, I don't know, here. My relative numbers are not exactly great, but and 13 might be here. So we're talking about this area now. So again, I need the length. The length is going to be, what, 13 minus 10? Of course, you would already know it's 3, but we're showing our calculations. The width continues to be 0.1 because it's the same for all random variable x between 6 and 16. So we get 3 times 0.1, or 0.3. The area under the curve is telling us the probability. All right, the last question actually gives us probability, a 50% probability, which we know that to be 0.5, right? That a customer will prepare a salad that's at least how many ounces? So the least would be what if it's 50% chance? Okay, we saw that that would be a 40% chance that they would prepare one greater than 12. So this question is saying, well, what's the number of ounces that we would get 50%? So again, if we use our area equals length times width, they're telling us area. Area is 0.5. Length we don't know, and width is always 0.1 in this problem. So if you divide both sides by 0.1, we'll get length equals 5. Now that's just the length. That's not telling us how many ounces of salad, but it said at least. So this number and above. So in other words, it's 5 and up. Somewhere, I mean, it's a length of 5 to go up. So in other words, if we take 16 minus 5, 16 down 5, we make a length of 5 here. Where are we? We're at 11. Right? So we found the length of this new rectangle is 5, but we're going at least so how far up? We go all the way to 16. So that must be from 11 to 16. 50% probability that they will make a salad that's at least 11 ounces. Okay, so this little exploration here is to help us understand area under the curve. We're going to do one more with the uniform distribution and then move on. We won't return to it. We'll move on to the normal distribution.